Welcome back to the next video, everybody. Today's video will be the final video covering examples of group schemes, and it'll be a real quick one today. So first of all, one of the most important examples of group schemes is the roots of unity group scheme. So this is bold mu sub n for n a natural number. And all it is it's the group scheme D of Z mod NZ. It's called the scheme of nth roots of unity over R. Now, if you take the dual of the exact sequence Z to Z mod NZ to 0, where the first map is just multiplication by n, and by dual, I mean take D of all three of these. We know from the last video that kind of turns this right exactness into a left exactness. And then by definition, we end up with an exact sequence from 0 to mu sub n to G sub m to G sub m. And so what does that tell us? That tells us that mu sub n is just the kernel of the nth power map in G sub m. Okay, and then naturally, I mean, this is the way I think about the scheme personally. For each R algebra B, mu sub n of B is just the set of elements little b and big B such that little b to the n is 1. In other words, it's all the nth roots of unity in B, right? Okay, and then because of this exact sequence here, we have an injection of schemes mu sub n into G sub m. And that corresponds under categorical equivalence to the R algebra map from R adjoin U inverse to R adjoin U inverse mod U to the n minus 1. This is sort of what you expect, right? You take the thing that GM is the spec of, and you create a quotient out of it in which nth powers are 1. Okay, and what this shows is, I mean, this injection shows that mu sub n is a closed finite flat subgroup R scheme of G sub m of order n. Okay, and so it's of interest because of the finite flatness. That's what this whole chapter is about, right? Okay, let's just make a few comments here about D of x. Take a finitely generated abelian group X. Okay, then you know from abstract algebra, X is isomorphic to a finite product of cyclic groups. This is the fundamental theorem. And so what that means is D of x then is isomorphic to a finite product of copies of G sub m and mu sub n's for various n, okay, just by the above discussion. And so D of x then is a closed subgroup scheme of G to the R sub m for some R by the above discussion. But then G to the R sub m itself can be viewed as the closed subgroup scheme of GLR consisting of diagonal matrices. This should sound familiar from like your linear algebra class, okay, just kind of viewed scheme theoretically. The upshot here is there's a faithful linear representation of dx, which identifies D of x with a diagonal closed subgroup scheme of GLR. And this is why D of x is called a diagonalizable group scheme. I don't think the D here is for diagonalizable. Maybe it is, maybe it's not. I think D is for dual here. But hey, both words start with D, right? So you can think of D of x as like diagonalizable or dual or whatever you like. I think it's supposed to be dual though. Okay, and then just lastly, I want to mention this P power group scheme. If P is 0 in R, so remember, so like spec of R here is kind of our final object in the category. And so if P is essentially 0 in your final object, taking P powers induces an endomorphism of G sub A. This should sound familiar. This is like a scheme theoretic version of what happens in an abstract algebra class. And the kernel of this endomorphism, denoted alpha sub P, is a group scheme. Easy to check. Okay, and for each R algebra B, alpha sub P of B is spec of Bx mod x to the P. So you're just killing off P powers here. Okay, and so next time we'll start building our way towards constant group schemes. So I'll see you then, and thanks for watching.